This video is over Chapter 35, the ratio test. So I want to talk a little bit about the ratio test itself. So we have a series that we have made from the sequence of partial sums from a sequence. And we apply the ratio test to the series by taking the limit as n goes to infinity of the n plus 1 term of the sequence divided by the nth term of the sequence. And one of three things will happen. The limit is equal to some number which is strictly less than 1. That implies that the series is absolutely convergent. If the limit is a number strictly greater than 1 or infinity, then the series is divergent. But what happens if the limit actually is equal to 1? Then your test is inconclusive. So we'll have to try another test. Another thing I want to point out about the ratio test is you'll see that nowhere here does it say conditionally convergent. Series are not conditionally convergent by the ratio test. The ratio test will tell you that a series is absolutely convergent, or that it's divergent, or the ratio test might be inconclusive, which means it doesn't tell you anything. So now we have two examples, and you'll notice they're both exponential functions divided by a factorial, or a factorial divided by an exponential. Whenever you see series with factorial terms or exponential terms, or a combination of exponential and factorial terms, this is a good candidate for using the ratio test. And that's because your exponents and your factorials reduce nicely. So for example, to apply the ratio test, we will take the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the nth term, but I'm going to multiply by the reciprocal of the nth term. We can take an absolute value. For this example, this is redundant. And here's why the ratio test is a nice test. Three to the n plus 1 divided by 3 to the n is 3. N plus 1 factorial divided by n factorial is n plus 1. So that reduced nicely. And so this limit is equal to 0, which is strictly less than 1. Therefore, this series is absolutely convergent by the ratio test. Now again, saying that it's absolutely convergent is redundant because these terms are always positive. But this series is absolutely convergent by the ratio test. From part A, we probably have a good idea of what's going to happen in part B. So to apply the ratio test, we will take the limit as n goes to infinity of n factorial. Take the limit as n goes to infinity of n plus 1 factorial divided by 2 to the n plus 1. This is the n plus 1 term of the sequence, and now we'll divide by the nth term of the sequence, or in this case, we'll multiply by the reciprocal. We take the absolute value. That's what the ratio test tells us to do, but again, for this example, that's actually redundant. But what happens here is this reduces nicely, just like this example did. N plus 1 factorial divided by n factorial is n plus 1. 2 to the n plus 1 divided by 2 to the n is 2. This limit is infinity, and so this series diverges. then the series diverges by the ratio test.